Welcome back to The Explainer. Okay, let's just dive right into this. Today, we're embarking on a really fascinating journey into the very fabric of our universe. We're talking about chemistry. You know, the captivating study of matter, its properties, its structure, and those magical, almost invisible transformations it undergoes every single day. I mean, from the souring of milk in your fridge to the rusting of an old iron gate, it's literally all chemistry at work.
So here's our roadmap for today. We're going to travel from the macro world we can physically touch all the way down into the invisible micro world of atoms. We'll hit matter classification, measurement rules, chemical laws, atomic theory, and finally wrap it all up with the mole concept.
All right, Section 1, Matter and its Classification. Let's jump right in.
Well, everything starts with matter, right? To visualize how things move within the three states of matter, think about a bus. Imagine you step onto a heavily crowded bus where you can't even move an inch to the left or right. That's a solid. The particles are tightly packed and simply vibrate in a fixed shape. Now imagine a half-empty bus where people can kind of shuffle around a bit. That's a liquid. It has a fixed volume but readily takes the shape of whatever container it's in. Finally, picture an entirely empty bus where you can just run freely from the front to the back. That's a gas, where particles are completely free to move with absolutely no fixed shape or volume. And keep in mind, these states can easily swap back and forth through processes like melting, freezing, and evaporation.
Zooming out a bit, we generally categorize all this matter into pure substances and mixtures. Pure substances, like water or a solid gold bar, have a strict, fixed composition. Every single molecule of water is always going to have exactly 2 hydrogens and 1 oxygen. That is a non-negotiable, fixed ratio. On the flip side, mixtures are exactly like a bowl of your favorite snack mix. The proportions are completely random. If you add an extra handful of peanuts or take out some pretzels, it's still a snack mix, right? You just don't have that strict elemental ratio binding the whole shebang together.
Moving on to Section 2, Measurement and Uncertainty. How do we actually put a reliable number on these physical properties so scientists around the world can agree? To solve this global communication problem, scientists adopted the internationally agreed-upon French Système International, or SI units for short, and there are exactly 7 base units. Whether it's the meter for length, the kilogram for mass, or the Kelvin for temperature, these 7 standard units are the ultimate foundation. Literally every single other measurement in chemistry, like volume or density, is essentially derived straight from these 7 base pillars.
Before we go any further, though, we really need to clear up a massive misconception. Mass and weight are absolutely not the same thing. Mass is the actual, constant amount of matter contained inside a body. It never changes no matter where you are in the universe. Weight, however, is a variable force exerted by gravity on that mass. So if you take a rocket ship to the moon right now, your mass stays exactly the same, but because the moon's gravity is much weaker, your weight would drastically decrease.
And since measurements in a physical lab are never absolutely perfect, we also have to deal with uncertainty. The absolutely crucial point here is understanding the subtle difference between precision and accuracy. Precision is simply how close your multiple lab ratings are to each other. So if you measure a liquid's volume 3 times and get 2.91, 2.90, and 2.92, you are highly precise. But accuracy is about how close your reading is to the true target value. If the true value was exactly 3.0, well, your precise readings weren't perfectly accurate. In science, you ideally want to hit the bullseye. You want both. To tame all that messy math and uncertainty, we use something called significant figures. It's essentially 4 simple rules that logically tell scientists which digits in a messy calculation actually mean something. Step 1, all non-zero digits are always significant. Step 2, preceding zeros, those little placeholders at the very start, they do not count. Step 3, zeros safely sandwiched between non-zeros always count. And step 4, trailing zeros at the very end only count if they sit to the right of a decimal point. This is how we logically filter out all that mathematical noise and keep our scientific data clean. Okay, Section 3, Laws of Chemical Combination. It's time to shift our focus to the strict mathematical rules governing how elements actually combine.
There are 5 historic pillars that define exactly how chemical reactions occur. First up, the law of conservation of mass tells us matter cannot be created or destroyed during a reaction. Next, the law of definite proportion says a specific compound always contains the exact same proportion of its elements by weight. Then, the law of multiple proportion shows that when 2 elements form multiple distinct compounds, they do so in small whole number ratios. Finally, we have Gay-Lussac's law for gas volumes and Avogadro's law, which connects equal volumes of gas to an equal number of molecules. Now, these aren't just mere suggestions. They mathematically prove to early chemists that the chaotic world of chemical reactions actually follows beautifully predictable patterns.
Let's move to Section 4, Evolution of Atomic Theory. It is finally time to look at the very building blocks of matter itself.
Our modern understanding actually starts with a man named John Dalton. Dalton proposed that matter consists of indivisible, indestructible little spheres called atoms. He boldly stated that atoms of a specific element are perfectly identical in mass and properties, and that they combine in fixed ratios to form compounds. For his era, this was completely revolutionary. However, as we all know, science is a continuously evolving process, and new tools inevitably lead to better understanding.
Modern atomic theory contrasts pretty sharply with Dalton's original ideas. We now know atoms are not indivisible at all. They can totally be split into incredibly small subatomic particles like protons, neutrons, and electrons. We also discovered that atoms of the exact same element can actually have different masses, which we call isotopes. And perhaps most mind-blowing of all, thanks to the concept of mass-energy equivalence, we now understand that mass and energy are entirely interconvertible.
But measuring something so infinitely small created a massive headache for chemists. I mean, how do you even weigh a single atom? Scientists realized they desperately needed a standard reference point. So they created the atomic mass unit, or AMU. They took the carbon-12 isotope, which is incredibly stable, and designated its mass as exactly 12 AMU. Therefore, one atomic mass unit is standardized as exactly 1/12 the mass of a single carbon-12 atom. It's the perfect, universal anchor for the entire atomic scale.
Finally, we reach Section 5, Mastering the Mole Concept. This is the ultimate metric designed to bridge the gap between invisible atoms and our visible world.
Let me pose a serious challenge to you for a second. How do we count something we can't even see? If I hand you just a single gram of table salt, literally a tiny physical pinch, and ask you to count the exact number of molecules inside it, where do you even begin? We desperately needed a mental and mathematical tool to handle impossibly large quantities.
Enter the absolute superstar of chemistry, Avogadro's number, 6.022 times 10 to the 23rd power. Just take a second to let that number fully sink in. If you wrote it out without the scientific notation, that is a 6 followed by 23 zeros. It is an absolutely staggering, astronomical scale. And this highly specific, massive number of particles is exactly what we call 1 mole.
So, the crucial point here is understanding the sheer utility and power of the mole. Think of it exactly like buying things in dozens. You don't ask a baker for 24 individual pastries, you simply ask for 2 dozen. The mole does the exact same thing, but for unfathomably massive numbers, simplifying them into workable, practical chunks. It acts as the perfect bridge, converting atomic mass measured in AMU straight into molar mass measured in regular grams, and it beautifully standardizes how we write out our chemical equations.
Now, if you are still struggling to truly grasp the sheer, terrifying size of a mole, consider this. A single tiny 0.03 gram drop of water contains 100 billion times more molecules than the entire human population currently living on Earth. If you distributed those microscopic water molecules to every single person on the planet, each person would hold 100 billion of them. That mind-bending scale is exactly why Avogadro's number is so profoundly necessary.
And this leads us to the elegant mathematical symmetry of chemistry. Molar mass is simply the mass of exactly 1 mole of a substance, measured in grams. And here's the beautiful time-saving part. It is numerically equal to its atomic mass. A single carbon atom weighs 12 AMU. But if you gather exactly 1 mole of carbon atoms, that giant Avogadro's number of them, it will weigh exactly 12 grams in your hand. The actual number stays the same, but the scale shifts perfectly from the microscopic to the macroscopic.
So how do we actually calculate this when we're standing at a lab bench? It builds into a very simple, straightforward process. Step 1, identify the given mass of the substance you're working with, let's say in grams. Step 2, determine its specific molar mass by just checking the periodic table. Step 3, simply divide your given mass by that molar mass. That's it. The seemingly intimidating math of chemistry really just boils down to basic division, allowing us to easily calculate the exact number of moles sitting right there on our desk.
As we wrap up this explainer, I really want to leave you with one final awe-inspiring thought. If a single microscopic drop of water holds more molecules than the entire human population multiplied by 100 billion, just imagine how many intricate, flawlessly timed atomic interactions are happening inside your own body at this very second. The invisible machinery of chemistry is constantly running, building, reacting, and transforming everything around us and within us. It's truly breathtaking to think about. Thanks so much for joining me on this structured journey from the visible to the invisible. And keep exploring.